Hello friends, in this video I'd like to solve 5 problems from the current edition, the current first round of Silesian Mathematical Competition 2024. So if you don't know about it, it's one of minor Polish mathematical competitions held in Polish Voivodeship of Silesia. It has 2 rounds. A few days ago was the first round, and on each round usually 5 problems are suggested, are given to the students. It's meant for high school students in Poland, and well, the level of difficulty is not very high. It's nowhere near Polish Mathematical Olympiad or other Olympiads, but some problems are rather not very hard but nice in some way. It's meant more for general but ambitious students of high school in Poland. Okay, so the first problem. We are given this system of equations. X plus 4th root of x equals y plus 4th root of y is one equation, and the second one, x squared plus xy plus y squared equals 1200. 1200s in other words. So here is my hint for this problem. Show that function which maps t to t plus root of degree 4 of t, that this function is increasing. So give this problem a try. Okay, so here is my solution. First let's write our assumptions, where we must assume that x and y are non-negative. Why is that? Well, because we are dealing with real numbers, and we know that roots of even degrees are defined only for non-negative numbers. Well, then let's notice that function t which maps t to t is obviously increasing. It's increasing, obviously. Moreover, function which maps t to root of degree 4 of t is also increasing. And that means that sum of these two functions is also increasing. It's also increasing, and moreover, so since it's increasing, strictly increasing to be added, since it's strictly increasing, maybe let's write it strictly. So since it's strictly increasing, it's also injective. Maybe let's write it in other color. So function which maps t to t plus root of degree 4 of t is injective. So if the values are the same, the arguments must be the same as well. Well, let's take a look at our first equation. Here we see that our function has equal values for some x and y, and that means, but by our first condition, x and y must be equal because of the injectivity. So x equals y. And now the problem becomes trivial, because our second equation says that x squared plus x squared plus x squared equals 1200. So x squared is 400, and since we are dealing with non-negative numbers, we have our answer. X equals 20 and y equals 20 as well. And it's the only pair of solutions. Very nice. Okay, and now our second problem. Let a1, a2, and so on up to an be integers whose sum is 2024. Find the remainder upon division of a1 cubed plus a2 cubed and so on plus an cubed by 6. It's slightly rephrased, but the sense of this problem is as in the original statement. My hint, it's also not that difficult, but you should compare x cubed modulo 6 and x modulo 6 for positive integers and see something interesting. Okay, so here is my solution. By the way, I have done a very similar problem, solved a very similar problem not that many days ago. A similar problem, slightly harder, was proposed on the Macedonian Mathematical Olympiad. I don't know which year it was. So let's notice something. First, 0 cubed is congruent to 0 modulo 6, obviously. Plus or minus 1 cubed, well, it's obviously plus or minus 1, so it's congruent to plus or minus 1 modulo 6. Plus or minus 2, well, it's 8 or minus 8, but 8 is congruent to 2. Minus 8 is congruent to minus 2. So it's congruent to plus or minus 2 modulo 6. And finally, because we have now considered 5 possible remainders, the last remainder can be 3, and 3 cubed is 27, but 27 is congruent to 3 modulo 6. And since we have considered every possible remainder, that means that for every for every integer x, x cubed is congruent to x modulo 6. And now our problem becomes trivial. So a1 cubed, a2 cubed, an cubed, by the property which I have justified, it's congruent just to a1 plus a2 and so on plus an. And we know that the sum of these numbers is 2024. So it's congruent to 2024, and it's congruent to 2. It's congruent to 2, modulo 6. Because 2022 is both divisible by 2 and 3. So we have our answer for our problem. So our sum modulo 6 must be equal to, the remainder is 2. Very nice. Next problem. Let a, b, c, and d be real numbers such that 2a minus b, 2b minus c, 2c minus d, and 2d minus a are all positive. We wish to prove that a, b, c, and d are positive as well. So my hint, chain our inequalities to show that d is smaller than something times d. And that should be sufficient. Okay, so here is my solution. Let's take a look. Well, let's enumerate our assumptions. So we assume that this is the case, this as well, and finally 2d minus a is also positive. Okay, and now what can we do? Let's take the third one. By the third one, d is less than 2 times c. But by the second one, so it's by the first inequality, but by the second one, c is less than 2b, so it is less than 4b by 2. The first one was by inequality number 3. By inequality number 1, we see that 4 times b, well, it's less than 8 times a, because b is less than 2a. And finally, by fourth and last inequality, a is less than 2b, so it's less than 16d. And after chaining it, we see that 15d is greater than 0, and after division, d must be greater than 0. And it should be obvious to you, but similar arguments work for every other variable. Every variable, in fact, is greater than 0. So, similarly, for A, B, and C. And that closes our proof. Okay, the fourth problem from geometry, planimetry to be exact. Let ABCD be a rhombus with an acute angle of measure greater than 60 degrees at vertex A. Let E be the point inside of this rhombus such that triangle BEA is equilateral, and let F be the point outside of this rhombus such that triangle BFC is also equilateral. We wish to prove that points D, E, and F are collinear, or they lie on the same line. So my hints for this problem: denote two angles by phi and psi, and show that their sum is 120 degrees. Also, a good drawing may be very beneficial. Here is my drawing. Well, not exactly mine, but let's make it smaller to fit. Not exactly mine, but not by hand. But here is a nice drawing of our equilateral triangles. So denote, for example, as I suggested, this angle by phi, this angle by psi, and show that these two angles add up to 120 degrees. So give this problem a try. Okay, so here is my solution. First, let's notice that some triangles are isosceles. Namely, we know that we are dealing with rhombus. Since A, B, C, and D is rhombus, we know that this segment has the same length as this segment. But our triangle BEA is equilateral. So these segments also are of the same length. And moreover, triangle BFC, which is in orange, is also equilateral, and since it's also a rhombus, our quadrilateral ABCD is a rhombus. BC is also equal to AB, and here we have another pair of equal segments of equal length. And we can see now that triangles DRE and triangle EBF are isosceles. And that means that if here is phi, here is phi as well. If this is psi, this angle right here is psi as well. Perfect. And now let's do some angle chasing. Here we have 60 degrees, here we have also 60 degrees, and here as well. What else can we say? Well, here we have 60 degrees as well. Here we have 180 minus 2 times phi. And finally, what is this angle? Angle EBC. Well, this entire angle is 180 minus 2 times psi. But here we have 60. Angle CBF is 60 degrees. So it must be the case that this angle is what exactly? It's 60 degrees minus 2 times psi. No, sorry, it's 120 degrees. It's 120 degrees minus 2 times psi. this angle right here. Perfect. And now let's notice something. Since we are dealing with a rhombus, we know that in rhombus, this angle equals this angle equals this angle. So the sum of an acute and obtuse angles are always 180 degrees. So now we can write that angle DAB plus angle ABC equals 180 degrees. And let's put phi and psi. DAB, this angle, is 200, or maybe it's 180 degrees minus 2 times phi plus 60 degrees. ABC, what is ABC? ABC is 60 degrees plus 180, 120 minus 2 times psi. And that equals 180. And now let's do some cancellations. 180, 180 gone. So we have 240 degrees equals 2 phi plus 2 psi, which means that 120 degrees equals phi plus psi. And that's all we needed, because if you now look closely, if we sum phi 60 degrees and psi, we get 180 degrees, which means that in fact we have E lies on the segment connecting D and F. So since, let's write it, since measure of angle AED plus measure of angle BEA plus measure of angle FEB equals 180 degrees, we know that E lies on the segment. It lies on the segment DF. And that closes our proof, because that exactly means that our triangle, that our points DEF are collinear. They lie on the same segment. Very nice problem, I'd say. Pretty easy, angle chasing for the win. And the very last problem of this competition from combinatorics. Problem number 5. Is it possible to partition the set 1, 2, 3, and so on up to 21 into sets A and B such that A has 2 elements, B has the rest elements, the remaining 19 elements, and the product of these 2 elements of A equals the sum of the 19 elements of B? So my hint for this problem, find a Diophantine equation in A1 and A2 where A consists of A1 and A2. So form a Diophantine equation and solve it, or see that it has no solutions. Maybe it has. So give this problem a try, and I will see you in a minute. Okay, so here is my solution. So let A equals A1, A2, and let B equal B1, B2 up to B19. And suppose for a moment, suppose that A1 times A2 is in fact equal to the sum of b1, b2, and so on. Now, since our sets partition the set from 1 to 21, we know the following: a1 plus a2 plus b1 plus b2 plus and so on plus b19. We have every element of our set counted once, so it's the same as 1 plus 2 plus 3 and so on plus 21. Very well. But now, by our assumption, this sum b1, b2, b19 and so on, it's just the product of a1 and a2. And what about the right hand side? Well, here we have an arithmetic progression. Well-known formula says that it's the first element plus the last element over 2 times the number of elements. And I wish to do one trick right now. I wish to add 1 to both sides of my equation. And we have, what exactly? We have 1 plus 11 times 21. Y, and now on the left hand side we have a nice product. a1 plus 1 times a2 plus 1 equals, and on the right hand side, if you do the calculations, you will have 222. 222. Now, we need to do a prime factor decomposition of 232. Well, it's pretty easy to do because it is divisible by 2 again, and by 2 once again. And our factorization is 8 times 29. You can verify it by hand or by calculator or something. Now, is it possible? Well, notice that if this equation were to be true for some elements of our set, that it must imply, since 29 is a prime, then 29 must divide either the first parenthesis or the second one. Is it possible? No. Why not? Well, recall that we are dealing with numbers from 1 to 21. From 1 to 21, so this number is definitely somewhere between 2 and 22. This number as well. It's somewhere between 2 and 22. And it's impossible for 29 to divide any such number. We get a contradiction. We get a contradiction. Which means that our set cannot be partitioned in such two sets, A and B. And that's it. That was the entire contest, the entire competition of this year. First round, as I said. Well, in a few months, there will be the second and final round, and I will also cover the problems from this competition once it's published. And yes, I hope that you've enjoyed this video. It was rather easy compared to some other problems which I used to solve on my channel, but I hope that some Polish viewers from Silesia might watch it someday and be inspired or something, whatever. Thank you for watching, and I will see you next time. Goodbye.